can go when you can.
Enough ads for Apple and then I watched. You guys see it with Michael Fassbender, Steve Jobs, movie Steve Jobs. Man, yeah, I was such a control freak. Eh?
Except for when it came to parenting.
He wasn't a control freak. That's what you see when you die.
I was just gonna say.
The infinite loop. The infinite loop. Go on. Yeah,
Oh, I see. She's just viewing me. Okay, so let's just go ahead and start. All right.
It's a matter of habit.
Right. So here's the. Here's the link.
What about on the side there? No, on the side, the where you have all your controllers. Yeah, the left, right, left. Like the, oh, that's your screen.
There used to be. Okay. Go to that. Go to that person. She knows me.
It's delaying on meetings too. I'm new to this.
Hey guys.
Hey, okay.
Perfect. And I think Dequan's trying to join as well. He
Okay.
met me in the other hangout. So
Oh,
okay.
This is amazing because like it's so easy to forget and things are changing, I guess.
Yeah. They did change. They did change a
I was
number.
nervous, like there's 4 people just watching me and what are you doing?
We don't let them think less of you, man.
Okay, so
Hey, Dequan.
Hi guys. Hey.
Hey, Dequan.
Hey. Let's go.
okay, so yeah, on my end I got two things. 2 items to talk today, and then first thing is that I kind of want to brainstorm what we got a SimPEG talk in SetJeep in 2 weeks. So SetJeep is more like they're focused on an environmental problem and geotechnical issues. So yeah, it's I've never been, and also like hydrogeology is quite big there. I think it's kind of depends upon the case. It's kind of smaller scale surveys. They're using something, but probably most of them on size. So I'm kind of interested, and those are different crews that I've never really had.
And for 1D too, right? They're probably super interested because most of their problems are
Yeah. And not only Omar, I think they do a lot of like long survey, like similar geometry, like this GEM EM31 types of survey as well. So they're more versatile compared to like in the oil industry. Well, I don't know, differences.
yeah. More diversity in the ecosystem.
Yeah, more diversity in that. Well, it's not in, like this talk in the education section, so but the top is I'll just no. I'm going to share the screen. Is that fine?
Yep, for sure.
Ooh, what's that?
The infinite hangout loop.
Yeah, so that's our talk.
Sagi, could you share that link in Slack?
Yeah, do.
Thanks.
So I missed the first part. So this is for which conference?
It's called SatGeep, Nikwan.
Okay, I see. Okay, yeah, I got
Yeah,
it.
you may know it, right?
Yeah, I know it. Yeah.
Have you been?
Not really.
Hmm.
It's in where is it? What's this? I can't
It's
remember.
it's in Nashville.
Oh, Nashville. Yeah, Tennessee, right?
Yes.
Okay.
I thought that's close, but that's pretty far.
Oh yeah, it's far. Middle of nowhere. Okay, go ahead.
Anyway, so so it's more like a kind of I don't know, like expanding the scope of open source software from research to geophysics education.
Mm-hmm.
And I was putting some sort of thoughts. I'll share this as well, but can you see this? Is that like?
Yeah, that's good.
Yeah. So first item is like kind of like it's a motivation, right? Like we're developing research tools, and then I wanted to show kind of what the research problem that we have in UBC, for instance. So I could like, yeah, I could use Thibault's problem, Dom's problem, Devin's problem, just to kind of like set the atmosphere. Oh, okay, this is like the research problem that we're dealing with, and then what has been developed with that, and then I think I can talk about SimPEG as well. So, so I think that part I thought kind of I don't know. So I'll share this doc later, and then if you guys can put some thoughts, that'll be good.
Sagi, also, do you want to introduce GeoSci as well?
Here?
Yeah.
Right.
I mean, maybe not right there, but
Yeah.
just like to put it on the radar.
So I thought so that was the first item, like developing geophysical simulation software to answer research questions requires pondering and posing access to details of implementation. So I think here I'm gonna kind of want to start with our research problem first.
Yeah, I like that.
Then second item, so I'm just following the Google Doc and then just putting some like a bullet points. Okay. The second item is, okay, now, well, tinkering with these pieces is where methodologies can be developed. So I think here, what are the scientific questions that we have? And yeah, here we can put some as an example, and then like how we develop softwares and stuff, like a little bit of histories, and like probably showing some example might be better than just talk. So if you guys have an idea about like something, just simple words fine, like some sentences fine, that would be great. And now we're like moving on to, okay, then how do we capture this, right? Like each of us developed stuff, right? Like it's a scientific question, sometimes solved, sometimes not, but their software developed with that. And then the question is, how do we like capture that, disseminate to the other people, and especially for education, I guess. So I don't know, I wasn't sure, and I was just putting things like a 101 toward one, like a level, because like there are different levels there are different spectrum people who want to do different things. I'm not sure we have tried for 101 types of course. I don't know. So, but the 201 to 301, I think 350 course, that's the DUX course. It's called Geophysics for non-geophysicists. It's mostly for geological engineering students.
Okay, yeah.
So that could be a good example. And here I think people like professionals who are from different disciplines and still want to use geophysics can be kind of fall into that category.
Is this an education talk or?
Yeah, it's an education talk. It's an education section, but geophysics education, I guess. What was the description about this? Sorry.
That's okay, yeah.
Yeah, that's an education talk. Yeah, so yeah, that's something that I'm not sure. Have you guys been to Bird's talk? So Adam gave a good talk about like a kind of this ecosystem of like a research consumer, research developer, and then how kind of like they're connected. And I think here we can bring up that similar types of concept here, because like say we're like sometimes, and that really varies. Like sometimes I'm research developer, but depends upon the case, I'm research consumer as well. So I think using that kind of concept here to bring it up, like how complicated is, what are the spectrum of people here, and what's needed to educate those types of people. So that was I think that's where I was. Yeah, I think then that sets up the motivation to like, okay, why SimPEG is important, how that can play a role.
So Sagi, what are like the biggest impact points you want to share with the community there?
I think on my end, I think this title, like that's what I really wanted to talk. I think what we develop as a research tool has a life, and then that can be kind of extended to all the food chain, like from researchers to all like even from to the public. Say, well, I think I'm not sure that's going to happen, but for like a one-on-one, like an undergrad level student, I think that's I think a main point that I want to talk.
Yeah, and so I guess like there's a couple exciting things within that I think you can try and bring up. So in the sense of like one of the things that we tried to do in the Jupyter talk and also in my SciPy talk last year, I think the analogy that we made might be too far afield for this community, because it was really like playing on the scientific software stack and then trying to treat education sort of as a part of that stack.
Sure.
So that makes sense if you sort of have the concept of a software stack already like understood and you get that, which this community may or may not. But there's two sort of interesting perspectives to take on that. Is first to take the perspective of the developer or the teacher in that sense. And so in that case, what's really nice about using your research software for this is it's something that you are familiar with. It actually is a chance to improve upon some of the things that are like within your research software, right? And then it's also sort of an avenue for sharing that with a wider community. Then when we go on the other perspective, thinking about a student or a consumer of the material, it's exciting having resources built on open source software because it really does provide you the opportunity to not only just like start from a textbook or a set of slides, but actually drill right down to the tools that people are using in their everyday research. And so I think that like both of those perspectives are worth speaking to and perhaps bringing up sort of right up front. Because what I see with just this first sort of walkthrough is it's very much telling the story, I think, of how SimPEG has evolved and seen use in education, which I think is super cool. So in the sense of like we built it for research and then found it to be useful in education. But I think like if you want to sort of do that, it's important to set out and just say that you're going to first start out by telling sort of the story of the evolution and then perhaps examine it from a couple different perspectives.
Yeah, I see. Okay, that sounds actually great. Yeah. Yeah, I haven't really started. I just like putting things, putting thoughts in here. So
yeah, absolutely.
Yeah, I'll share this. I'll kind of transfer that into Google Doc and share it with you guys. So
cool.
I'll appreciate your thoughts on this. Yeah, well, this will be kind of cool. It's a new area. Not really new, but it's like we've never met these people. I think probably I can contact the guy who suggested this talk, right, Lindsay?
Yeah, yeah.
I think I'll try that as well.
And do you know, like, is it mostly a research audience, or are there industry professionals who are also there?
I think my guess is a bit of both.
Okay.
But considering that's an education section, I don't think a lot of professional will be there, I guess. Most researchers, I guess. So I think we should probably like kind of tailor it into more in a researcher side.
Yeah.
But just one more comment. As far as I know, so this conference is mostly for the near surface, both for the research and the industry. But the near surface industry is relatively small, and they're poor. They don't have much money. So basically, the kind of open source software is perfect for them.
That's a good point.
Exactly. So for the near surface project, sometimes it's only like a few $1,000 or maybe like $20,000. That's very, very small. Yeah, so I mean, we're working with the SimPEG or similar like open source software is basically perfect.
That's great. That's great.
They're not like oil companies; they don't care like spending $1 million to get the software.
Yeah. I hope they're getting a little bit more money because I think the water side getting more attentions in these days. I think so they are getting better, but still not even like not compatible at all with the oil and gas or even minerals. And
one of the things you could think about doing. So I did this at the Reflex presentation, and I think at the SciPy one, is bringing up one of the apps if you want, if you're able to use your own computer.
Yeah. Yeah, I'll check with this guy. I think he's a chair, I guess.
Yeah, and like for me, what I didn't run it on Azure because you never know like if internet connections or whatever are gonna work or not. So I ran everything locally. But the 2D cylinder one is really nice for explaining like you show current channeling and then you show the charges and the resulting potentials, and that's what you measure.
I don't exactly remember did you use the apps or more like a notebook form?
I used the apps. So for the Reflex, I used the apps. For SciPy, I also did. So the SciPy one is I think a decent example. So I used the 2D cylinder.
Right.
And I started I made it conductive because that's an easier thing I think for people's heads to get wrapped around.
Yep.
And then you show the currents and you see the currents like being sucked in, show the charges and then show the resulting potentials. And then that's the data that you measure on the surface.
Yeah. Yeah.
And so that's it's a reasonably quick demo because you don't want to go too long with demos, but that one is pretty quick. And it's cool to then, if you've sort of already introduced SimPEG, to then basically say every time I clicked a button, I ran a 2D DC simulation. And that's pretty cool.
Yep. That sounds good. Okay. Are there any suggestions or comments? Okay. If not, thank you very much, guys. Yeah, I'll put more thoughts on it and then probably try to build up a presentation with Google Slides and share with you guys.
Yeah, that'd be great. And there's a whole bunch of resources, anything that you want to use from any of the previous education style talks that we've given, that all should be in the SimPEG presentations folder.
Great. Those are those in MIT license, Lindsay?
They are Creative Commons.
Okay. Thanks.
Yeah. Open source content. Absolutely.
Okay, so that was the first item, and the second item that I wanted to talk is the. So I was working with Dom, and Dom poked me. Okay, why don't you develop a kind of 1D EM1D code, but using parallelize that and use a lateral constraint. So I was working on it. So I take a crack on it. I finished it for frequency domain. Time domain is a little bit more complicated, but I think moving to time domain is not going to be like a really big deal. But it's going to be a little bit more slow, more computationally expensive. But I think that's kind of fine. So I think deep one here, I used the multiprocessing. So I think this presentation may answer your question as well.
Great.
Okay. So I'll first show you example.
Mm-hmm.
And
you make the font a little bit larger.
Yeah. Let me see if I can zero it in.
Command plus.
It seems like you're reading my mind, Lindsay. I'm just impressed.
Yeah, great. Yeah, looks good now. Yeah.
Okay, so I'm thinking about the resolve system here.
Mm-hmm.
So there are 5 frequency from 300 to like a 400 to 1300, 330,000. I guess. Okay, then I generate the model. Looks like this.
Mm-hmm.
It's a little bit of details, but I just comment with Dom because ordering is like a little annoying because SimPEG ordering is in X then Y, but here this totally doesn't make sense. Because 1D, you always go Z down right, and then you got multiple sounding. Then ordering in X and Y that doesn't make sense. So here I'm doing Z. I'm going back to UBC format, which is terrible, but that's fine.
Sorry. Can you run that by me again? I didn't quite.
Oh, so here, okay. So showing the code. So I'm generating. Can you see here?
Yeah.
Cell 4.
Yeah.
So I'm generating sigma in SimPEG mesh. This is 2D mesh. Okay.
Mm-hmm.
Then I'm changing the order with the like that. It's kind of like a UBC order. Does that make sense?
Oh, okay.
But that's fine. I think here there's a difference. Here mesh doesn't really. I'm not even using any mesh in the problem class because I don't need that.
Yeah.
Okay. But when I'm sorting my sensitivities and data, I'm using that order of Z down first and then go X, right? Because you want to order in one sounding, then move to the other sounding. So that's why I did it. It took me a while to figure it out.
So, but by the way, inside the SimPEG, if you're working with the code, it's actually still counting X first, then Y, then Z. It's still following the order, right?
No, but in the code, I'm not using any mesh here.
Oh, okay.
I don't have any mesh going on because it's a semi-analytical problem, and then I don't need any mesh, right? Okay. So I think here mesh is just some sort of a artificial thing that I want to generate some model.
Container.
Exactly. That's a container. Okay. So this is the model, 1D model. So I got a conductive overburden. I think that's a 50 ohm meter. Background is 100, and I got a target looks like this, conductive target. It could be I don't know. Yeah, seawater, maybe. So far, so good?
Mm-hmm.
So now I'm generating a survey geometry. So I got the X, Y, Z locations. I got RX location, source location, and topography. Okay, so it's 30 meter above the topography. It's transmitter and receiver. Okay. So here, I'm not sure that's a good way, but the X and Y doesn't do anything for RX and source location. So only Z matter here. Mm-hmm. The RX, X and Y is just some sort of just a container. But sometimes that can be useful later that when you're thinking about 3D problem. Because I don't need that at all in 1D problem. I just need an offset. That's it. Okay. So now I'm forming a mapping. So I'm using exponential map. Okay. So I got here, my model is a conductivity value for every sounding. And every sounding has the same number of layers. Here, 19 layers, for instance. So let's say I got 20 sounding. That's actually then 380 models. Okay. And that's the survey. So that's what I call global EM1D survey, FD, frequency domain. Not sure that's okay with the name convention, Lindsay. You can comment. definitely change.
So, but this global EM1D survey FD is a class you just defined, or it's in SimPEG, or it's just your personal?
It's in my personal Git account, but open, so you can use it.
Okay, I see.
I think it's under SimPEG. So under SimPEG, there's a SimPEG EM1D.
Okay, so maybe one day, once this one become mature, you can merge it. Okay.
Yes. I'm not sure where to bring in, because it could go to GeoAna or like a SimPEG itself. I'm not sure, but
yeah, that's a good point.
We can decide.
It can even be a standalone stuff. Like that's okay. Yeah, just I know the organizational thing.
Right. So I'm not totally sure where's a good kind of place, but at this point, I think it's just in my kind of private account. But I think it's public, but it's under my account, I guess.
Okay.
Okay. So the survey takes RX location, source location, frequency, and offset. So offset is an array that same as number of frequency. So each frequency depends upon the case. They have a different offset. So I just made it as a variable. Resolve is actually same. So it doesn't matter, but the dgem is different. So I think we need some flexibility. And the source type, I have a vertical magnetic dipole only, and or a horizontal loop. So I got two options. I don't have a horizontal magnetic dipole. So if you want to do a coaxial, we need more development, but I'm not going to at this point. I'm not sure that's really helpful for 1D, because I think that's pretty susceptible for speedy structures.
Yeah.
Anyway, and the field type is secondary, so you can choose either total and primary, and the topography. So that's what the survey takes. So I think here most of the information in the survey, like a problem doesn't it's pretty light. I think you can have a parallel with what was his name? Mexican guy.
Dieter.
Yeah, Dieter's stuff. I think it is pretty similar. Okay, now problem is called global EM1D problem. This is just a kind of some sort of a abstract thing, which calls the subproblems. I can show you later. So I put just the empty list for mesh, because it doesn't do anything, but it still needs to put it in because of the current SimPEG structures. And for sigma map, I just put the exponential map. HZ is the vertical discretization. So I think I got a simple function here that you put the frequency and the sigma background. It can compute the HZ. So I'm using the skin depths idea to define the smallest cells and the deepest depths. Okay, so I think that's what it is. And then you pair it with survey. And here you can choose either parallel or not. Mm-hmm. So yeah, if you choose parallel, it uses multiprocessing. And my machine is only 4 cores. And while other cores working hard for other things like a Google Hangout, it's a pretty expensive process. So I think 2 is the maximum that I can use. Greater than 2 doesn't really help. But I think my Linux machine, for instance, I got the 8 cores. I think I can use 6, which is actually pretty good. So I think just here, I think it's not gonna be really fast. But if you got a good machine, your performance will be pretty good.
I told you,
so maybe it's worthwhile take a look at what's inside your global EM1D problem.
I'll show you later.
Okay.
I'm just I want to give you just
that's good.
You. And here I'm setting the model. M is log sigma. Okay. And I can for model. So I think that's actually pretty fast. I think, so yeah, it's less than a second. And then I think, and sounding. Okay, I only got 20 sounding here. So I think that's the reason why. Mm-hmm. But I think I ran 1,000 sounding. It takes about 5 minutes for inversion. So it's not too bad. Okay, so that's how the data looks like. So the black is the real and red is the imaginary. Okay, that's the formalling. Now I'm moving on to inversion. So here, this is something that I haven't finished it yet. So in the problem mesh, I don't have any mesh. So in regularization, that's where you need to think about, okay, what is my mesh and how I'm going to regularize this sounding locations. So here I'm just simply using, just like assuming everything is rectangular mesh and no topography. So it's a simple case, but we can easily expand this to when you got topography, complex structures or stuff. But it's kind of like a demo. And it's a similar setup. Like you set the floor, standard deviation. Initial model is 100 ohm meter. And I'm using actually DOM's LPLQ inversion or sparse inversion. Is that right? What is the name? Craig called LPLQ inversion. What do you call?
I never liked LPLQ.
It's a sparse inversion?
Sparse.
Okay, sparse inversion. So I set the P is equal to 0 and then Q 1, 1. So P 0 means that we're like looking for a very sparse model in the model space, and the Q means like the gradient space. So I think I can run. So it's running now. It's decreasing.
Mm-hmm.
Yeah, it's not gonna take that much time. Anyway, so here I set the alpha S1 and alpha X and alpha Y to 0. Here alpha Y is more like a Z direction.
So Sagi, the model in this case, is it just like a stacked?
Yes, exactly.
Okay. And then so your global problem then knows how to map each, like how to grab its correct model?
Right.
Okay.
So I have a certain order. So I think my ordering is first like a sounding first, then the layers.
Okay.
And
then for the regularization, have you
for the
put
regularization, if you see my mesh reg, it's opposite order, right? Like mesh.hy, then mesh.hx. So I'm like the ordering, and then well, I think we'll make it better, more transparent.
Yeah.
For actual development. So Dom is working on it. So it's finished. I think it takes about a minute, but I think kind of expanding to 1,000, it's not linear. I think it's going to be much faster because there are a lot of like communication going on, but the problem large is not that much. So
the communication is mostly from your local 1D problem to like a 2D container. Is that right?
No, I think I'll explain that later because I think showing the code is a little bit better in that sense. Okay, so I think if you guys haven't used the DOM sparse inversion in the inf problem, there's L2 model because I first find the L2 model, then start to kind of sparse inversion. So there's an L2 model, and also the final one is the sparse inversion result. Okay, so this is a true model.
Mm-hmm.
Okay, and then that's L2, which is pretty good, right? Like we find the first overburden. The thickness is not great, but it recognizes it's there. And then it finds the resistor top and also finds the conductive layers or conductive seawater. Okay, now I put the sparse inversion, and then it shrinks a lot, right? And then actually it gets close to the true value, which was 0.1. And I think this two images actually kind of great because like it tells you, well, your problem, like your model is non-unique. And then the bottom part, we don't really know. So I think just showing these two images, like saying, oh, okay, what's the uncertainty? We don't have a really quantitative values, but just seeing that, I think it's nice. And fit is okay. Yeah, so I think it's nice. And I think this is kind of cool, right? Like you develop one thing, but you can plug in what's developed here, which makes it like, I don't know, this research process really fast and more exciting. I don't know, once I finished that, okay, what's my motivating example? So I first did the L2, then, okay, can we make it a little bit better? And then I was, yeah, okay, with DOM sparse inversion, I can plug in and run. I don't know, this is actually really exciting part on my end.
Super cool, Sagi.
Anyway, so that's kind of like a motivating example. I'm going to show you how I did the parallelization and a little bit of.
Yeah, what tool set did you use?
Yeah, I'll show you here. Okay.
I'm actually going to ask you that today. Where that is.
Can you see that? Is that fine?
Yeah, that's fine.
Yeah, that's good.
Okay, so you may like it. So I'm using, it's a little bit of detail. So this is okay, everything is in the like a frequency domain, even space. So you need to convert that into like an actual spatial domain. So you need a Hankel transform to do that. So what I used to use, I wrote like a small code that I got somewhere, and then I found Dieter has a better code. So actually, I used the better Dieter's Hankel transform here, which is nice. Anyway, so I'm
which package has a better digital filter?
EMPI mode. That's
EMPI mode.
Dieter developed, and it's basically same problem. And then he has more sophisticated code. Here I'm very focused on certain application. And
so just one note, that's kind of interesting. Yesterday I was chatting with Kerry, and he was actually authoring the paper with the author of EMPI mode.
Oh, okay.
Yeah, and they published a paper on the digital filtering, and they managed to have like a bunch of very nice a new set of parameters.
Exactly. So it's a actually Kerry published like initially about the Hankel transform in geophysics, and he opened up the code. I think that Dieter actually took what he has done and then probably made it better, I guess. So.
Yeah, so I think they made it even better in the upcoming paper.
And then that was the reason why I could speed up a lot.
Yeah, okay.
I used like there's a different version of the filters, and then I used just like some specific one, and actually that's nice.
Yeah, I'm not sure whether it's implemented in the package, but it sounds like you have the control, like how many coefficients you want, what's the accuracy you want.
Exactly. So there are multiple, like a set of coefficient that you can choose. So depending on the case, I think you don't really need that much coefficient, and you don't really need to use that.
Okay.
This should be a good first just for you that you pieced out blocks and created them code from someone else's package. Like this is huge, man. Like started building a code base out of everybody's code. It's rare. It's really rare that you read stuff like this.
Yeah. Okay. That sounds good. Okay. So there's two main files in here in the SimPEG EM1D. So the main class is a global EM1D problem. Okay. So this is what it does. So I think here you can see, okay, it checks whether you have a multiprocessing or not. If not, we set the parallel false, something like that. And I think I can show you this formalling class. So this you can see sigma. So here sigma is just the values has a certain ordering, and I set that as a property.
Okay.
So it's like now it's like a matrix.
Oh, okay.
And then every time I update this property as well. Okay, when I'm inverting it. So now for it, so there's no fields here, so I'm not not really using the field class, but here's a forward class. And then this is where parallelization happening. It's just pretty simple, Dequan. So what you do, so you set the pool, and then you pass the number of CPU that you want to use. Okay, then you're looping over. So pool.map is like it's looping over. You pass a certain function and the input arguments. Then it can loop over. So it's a list comprehension, and I think that's it. So it loops over the list, then it actually evaluates the function and outputs the whatever outputs that your function has.
So basically, it uses a dynamic scheduling, or
you can do it. So you can tell like this is a synchronized version, but there's async. Then you need to figure out the ordering. So here I need a certain order, so I didn't use it. But if you don't care about that, you can actually use asynchronized version. So I think that's the core. And then I think this is the core function run simulation FD. So I generate the EM1D simulation, and it's nothing but a function that takes some arguments. So here I'm taking a bunch of arguments, Rx location, all the. I think here we can use the serialization, Lindsay. So then basically what it does, in that function I generate the survey and problem every time when I'm calling it. So in that way I don't need that much kind of like a communication. So I think it's almost like embarrassingly parallel. And that's kind of easy. So if that's the case, I think parallelizing other SimPEG stuff, it's simple.
And
then,
Sagi, is this where EMPyMod is called, or where do you?
Oh, EMPyMod is not called here. So it's in the, so this is the like a core class, EM1D. So this is where all the kind of evaluation happening. And then this is like where I'm calling the EM, like a filter type key, carry key 101. So that's a 101 filter.
Yeah.
So 101 means, but it's like a 101 coefficients.
Okay.
So what I'm doing, I think I can show you here. So this is where I'm calling the EMPyMod. So it filters that key, right? So I think there's a 201, 801. So I used to use Anderson 801 filter, and then that's actually the most used one. And it's expensive because it's 801 coefficients.
Okay, yeah.
8 more times expensive than 101. I think I tested the accuracy with 101. That's actually pretty good. So yeah, I just used a key 101. But that's an input parameter. So if you have a different case where the coefficient, you need more coefficient, you can change that.
That's super cool, Sagi.
Okay, so that was the, so I think that this is actually core function, the run simulation FD. So for time domain, we just need that run simulation FTD, then we're almost gone. Okay, I'm going back to global EM1D. So that was a 4 problem. And then well, we're using gradient based, so we need to compute the J. I think doing JVAG and JTVAG in this parallelization sense, that's not very, kind of not aligned well. So forming J is much easier in this sense. So for like usual stuff that we do, I think we need to figure out how to parallelize. Anyway, so here get J. Well, it's basically same. I'm just calling like a same function, but I'm putting the switch, Jacobian switch to true. So that actually evaluates the sensitivity and outputs. So I can form J in a parallelization, like a parallelized sense.
And here, do you have analytics sensitivity to find any difference?
Yeah. No, I do have an analytics sensitivity.
Okay, cool.
Okay, and then so JVAG and JTVAG is pretty simple. Like, but here you can also parallelize, right? Like a JVAG and JTVAG is your J matrix is not that big, right? Like it's a number of layers by a number of data. So you can actually parallelize that as well. Also JTVAG.
Nice.
Yeah. If you don't do parallelization, what you can do, you can form like a block diagonal matrix for J. Because it's pretty sparse if you think about what's that. And yeah, so I think, and for the update, so field is nothing. Here it's just a container because like in the problem it calls it. So I'm just putting like a container for fields that's doing nothing.
Okay.
So for this kind of a EM problem, because you're doing for the modeling sensitivity calculation in 1D, but your model domain is like a 2D section. So you actually know which column in your sensitivity matrix.
Exactly.
Non-zero, 0, right? So you know exactly pattern.
Yeah. But the similar idea can be used for 3D problem if you like know, okay, this part of the sensitivity does not really matter. We can work that out and like a user.
Well, yeah, the things for 3D is not as clear as for this case, because for this case, you assume you're only going to do 1D for the modeling. So you know exactly which element is exactly it's not.
Yep. Yeah.
There's a little bit like a shady area where you maybe not.
Exactly. Yeah. So that's yeah, it's an open question. And for the update, I delete the sigma and J matrix every iteration. So I think if you guys doing nonlinear inversion, this part is kind of important because like there's something stored, and then whenever you update the inversion, you want to delete it because like you don't want to reuse it. And then
Doggy, one thing you might want to do. Oh, I guess you're not using any of the mass matrices.
Nope.
Never mind. Okay, cool.
Yeah, so and then this is a global EM1D survey. So, well, I have a kind of a container for the calling all the problems. I also have a container for a survey as well. So this is a global survey, which is pretty simple. And then dpred is actually just calling the problem.forward. And well, like each small local problem has the one receiver point and one source point, but the global survey needs to know all the receivers and sources and all the information. So I think you do need that kind of class if you want to do the similar things.
And that's probably where I'm going to start there when we start adding topography, right? Where we start the indices of the
Yes.
mesh.
Yes. 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 So here the topo, I think that's now X, Y, Z. Well, I think that was the reason why I put the like a kind of dummy XY points. I think that's kind of good to have it.
Yeah.
And then, but I think that doesn't necessarily has to happen here, but it can happen in the regularization because like for a problem doesn't really need any of those information, right? So
if we don't change our
number of layers.
So you want to work it with a fixed?
No, I think a number of layers is fine. I think if you want to change the number of layers, that's fine. We can change the code, but I think it still doesn't really need to know X, Y points. Right? Yeah. Okay. So I think that's where I am, and I think it's working. And so I'm gonna like just try to apply that for book pronoun and see how that looks like. So that's the next things to do. And once that's working, so I'm gonna probably ask them to work on the regularization part. And once like that's done, I think we can move on to time domain.
Nice.
Nice. This is really exciting, Soggy. Would you mind just sharing the GitHub link of where this is whenever you have a chance?
Yep. Yeah, I'll do that right after this.
Cool.
Okay. So I think that's all I have.
So in your example, so you just show like you run like a 200 something microsecond for the inversion. So that's just using 2 cores on your laptop, or?
No, I think it wasn't 200 microseconds. That was about a minute.
Okay.
But yeah, it was only 2 cores. But I think if I bump that up to 1,000 sounding, it takes about 5 minutes for that inversion.
Yeah. Have you done any like just quick test of scalability, like not large number, but like you're going from 2?
No, I think I was testing this about 100,000 sounding. So
I mean number of cores, the number of like.
I used my Linux machine, which has 8 cores. So I used the 6 cores. I think that was a maximum. So I cannot like it doesn't really scale up to the maximum cores. I think. Yeah. It's like your computer. Well, I think that like the cluster, I think might be fine because it doesn't use anything.
Yeah, if it's dedicated machine, you can run all of them.
Right, yeah. Right. But your usual like laptops or computer, like using other things,
have something running.
Right. Yeah. So I think it scales up pretty nicely, and then I think that's better when you got more sounding location. Because if you got only 5 sounding location, yeah.
Just the same file.
So there's some sort of like a kind of step that you need to wait until that scalability works.
One thing to note too, I ran a sensitivity calculation on the cluster last week for the when we were playing around with the abstract, and multiprocessing actually, like if you don't provide the number of cores, it just figures it out. It figures out how many it can grab and runs it. So just in terms of default, I would suggest like actually putting none there and let multiprocessing figure it out. You don't necessarily have to require that the user inputs that.
Yeah, so I think if in my case, if the user don't put anything, it checks the maximum cores that you have.
Okay.
And I think that's what multiprocessing does.
Yeah.
It checks the maximum core and use that. Only reason why I use it here, because like that's slower than using 2. So that was the only reason why I put 2.
Yeah, that's fair.
If that one is sharing the information with everything else and doing everything else in the computer, you're waiting for that one to finally finish while all the other ones are free to have done it.
Yep.
So I can probably run your notebook on my machine or on PC with the whole like multiprocessing with the.
No, but I think you could just put it. You can put,
script.
no, but I think if you put that under the main, even in the notebook, so you just put a
main in the notebook.
Yeah, I think that'll be fine, I guess. So for Windows users, for the multiprocessing specifically, you need to put the under the main So you need to put first if main, blah, 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 then you put statement under that. Otherwise, it's not going to work. There's some reasons why, but yeah, it's important to just like let you guys know.
That's kind of also what I wanted to ask you about today, with where the multiprocessing is, because I was looking at the Python side, and they were saying, oh yeah, it works perfect on Windows and PC, but then if you, oh really? But then if you try to do a Mac or Linux, it just completely crashes, like it doesn't really work very well.
Really?
So then I was like, oh, hopefully you're going with MPI or something like that. But so MPI you just need to add that in and then it's fine.
MPI, so there's another package
Oh.
that use basically same pool structures, like because MPI is really not really designed like something like this. Because somebody actually wrote the wrapper that used the MPI for Pi, but using the same kind of pool, remember that's pool structures. And then so I think so here we want to really scale up to multiple clusters. Yeah. We can do it. So I think we just need to change that the if statement. So if you got a MPI pool package, then we can change that. So I think at this point we're not like so we're using a single cluster is kind of enough.
It's already distant.
But okay, now let's say what Dequan suggests. Like, okay, we want to invert the full Canada. We got millions of transmitters, sounding location. We probably need multiple cluster. Then
that's cool.
Yeah, but I think even my Linux machine, I think using like 100,000 sounding, I think that was okay for site, which is fine. I think at this point. Okay, I think we probably need to wrap up. Is there other things to comment?
There's one quick request I had. I started a pull request for the parametric map that we wrote, Sagi, for the block. I was wondering if you wouldn't mind just taking a look at it, and if you're happy, we can pull that in. It's a pretty lightweight pull request.
Right.
But I changed some of the names too. So trying to use the standard naming convention like parametric and then whatever it is afterwards. So parametric block or parametric layer or whatever the model is. So if you don't mind taking a look at that, I would appreciate your thoughts.
Sounds good.
Cool.
Is it you got 2D, Lindsay, or that's a 3D?
It'll work for 3D.
Ah, nice. Yeah. Great. Okay. I'll do that.
Thanks.
Nice.
All right.
Cool. Pretty cool. Thank you.
Thanks, guys.
Cool. Thanks, guys.
See you next week.
So you tried